Hello everyone, welcome back to this course on reinforced concrete design. We are in week 2 and this is our first lecture. Now the theme of this week 2 lectures are limit state design, but before that let us quickly review what we have learned in the previous week, because that will help us to justify why we need limit state method of design and what are the modifications that we are going to apply over the design concept that we have already discussed. So let us quickly go through. Now we talk about concretes because that's the main material we are going to use, and it's made of, as you can see, three different materials. The first one is cement, then the next is aggregates and water, right? And you can see the desired properties of concrete here. We already talked about some of the properties. For example, compressive strength, tensile strength, although concrete is very weak in tension, but still it has some value of tensile strength. Then shear strength, bond strength, durability, etc. Right? Now, how do you define concrete mix? We have already discussed. It is M, that stands for mix, and the characteristic value, right? For example, M30 means the characteristic strength FCK is 30 Newton per millimeter square. Of course, for that we have a very standard procedure. We have to cast concrete in this cube mold of size 150 millimeter by 150 millimeter by 150 millimeter, and we have to consider 28 days strength, because the moment we pour concrete, and there is a very specific procedure that is described in the code, then slowly it gets hardened, and as time passes by, every day it gains strength. So at 7 days we have certain level of strength. At the end of 28 days, the strength that we get is basically the design strength. And for that, what we do, we take this concrete cube, which is properly cured, and then test it in this machine where we apply compressive force and then find out the strength. Now, obviously, there is a very specific clause in IS 456 to define that strength. And for that, we have also discussed that what we need to do is we need to test number of cubes, and then for each cube, we need to find out the strength. And with the help of that data, we need to plot this curve. Now, obviously, this curve, as you can see, it is spread over a region, and that means it has higher standard deviation. Now, obviously, we will try to go for this very good quality concrete. The reason is, here you can see the dispersion of this data is very small. That means it is having low standard deviation. Now, how to find out the FCK value? We have also discussed that it is the point below which the area here is 5%, right? So if we cast samples and then test it, only 5% of the samples are allowed to fall below this value, and then we consider this value as FCK. And as you can see, here is the expression. So what we have here is the mean value of the concrete, and then from that mean value and standard deviation, we can find out the characteristic strength, and this K, which is a constant, and the value of it is 1.65, provided this is Gaussian, right? Now, for compressive strength, again, we just let us consider this example. We need to actually test some cubes. So if you have, say, 100 cubes, and these are some of the values, as you can see, and then if you take the average of this values and find out FCK, and if it turns out to be 28 Newton per millimeter square, then in code, actually, you can see that these values are in the interval of 5, and we have M 15, then 20, 25, 30, and that's how it actually increases. And there are different grades of concrete prescribed in Indian Standard Code. Now, the compressive strength of concrete can be carried out in two different ways. We can go for this cylinder test, or we can go for this cube test, right? Now, if we apply the compressive force over the cylinder, you can see it fails with a specific pattern. You can see the dotted line, and that indicates the region of influence, right? So we have to cast 300 millimeter high cube with 150 millimeter diameter. In case of cylinder, in case of cube, it is 150 by 150 by 150. And the relation between the cylinder strength and the FCK values is given here. As you can see, it is 0.8 times FCK. Now, if we go through the stress strain behavior of concrete, this also we studied. It is initially for a very small region, it is linear, and then we have curvilinear stress strain behavior, as you can see. And it's say starts with M20, and if you go up to M50, that's how schematically the behavior is observed between stress and strain. Now, out of all this, obviously the first thing to be noted is they are linear and non-linear with a very small linear portion at the initial stage. And then the most important thing is 0.2% strain. Corresponding to this strain is where we find out the effective compressive strength, right? Now, modulus of elasticity and brittleness, both of them increases as we increase the grade. For example, we have here M20. So from M20, if we go up to M50, obviously the Young's modulus will increase. We have already discussed that relation. I will come to that in a minute. So we have this nonlinear behavior between stress and strain, and the main point here is this one. And also one more issue is there. We consider up to 0.0035, and that's the strain level we always refer to at the time of failure. We'll come to that in a minute when we'll draw the block diagram. Now, if we consider the tensile strength of concrete, then it is very difficult to apply direct tension, because for that you have to have a sample where we have to apply this direct tension, and that's the reason sometimes flexure test is carried out. And normally this tensile strength is about 7 to 15% of the compressive strength, and you can easily notice that it is very small compared to compressive strength. Right. Now, for this flexure test, we have this kind of arrangements where we apply equal amplitude force at these points. If we have a center to center length between say supports is 600 millimeter. So at 200 millimeter from the two ends, we apply this force. There is a very specific reason for that. Let us consider this diagram again. And if you draw the bending moment diagram, you can easily see that between this load, if we draw the bending moment diagram and shear force diagram, there is no shear force here. However, there is a constant bending moment here. And we already know the flexural formula, which is M by I is equal to sigma by Y, where Y is the distance of the extreme fiber. So under this loading, obviously, we'll have a sagging profile. So the beam is going to sag like this. And then what will happen? At the top, we'll have compression, and at the bottom, we'll have tension. And therefore, in between somewhere, we have a plane where there is neither tension nor compression, and that is what is called neutral axis, right? From this neutral axis, this extreme fiber has a distance of y. Now, because we know this load P, that's what we apply, and we also know the dimension. In this case, we have 150 by 150. Then we can calculate the moment of inertia, and we know what is this PCR, and then from that we can find out this flexural stress, right? And that's how the tensile strength of concrete is measured. Now, with that background, let us quickly take an example how we actually use the block diagram to find out the stress profile. So what we have here is, again, the tensile strength based on compressive strength is given by this formula. It is 0.7 times square root of FCK, Newton per millimeter square. Now, if we consider a beam of size say 200 millimeter and 300 millimeter, it's made of M20 concrete, then if we need to calculate the cracking moment of the section, we can use this flexural formula. And we already know FCR is given by this expression. So for this concrete of M30, we can find out what is FCR, and it is 3.834 Newton per millimeter square. And then for a moment of inertia is for this cross section 450 into 10 to the power 6 millimeter to the power 4, and then from there we can actually find out the cracking moment, right? So that's very simple example, but we are going to use this concept in our design, but we have to consider exact stress strain behavior where we'll consider concrete and steel. So there will be some steel here, and we'll see how we can modify these expressions and find out the moment of resistance for that particular section. So that we will do for limit state design. We have already done that for working stress. We will do that for limit state. Now, sometimes for this plain cement concrete, we also test cylinder load. Okay. Now, for that split tensile strength, the tensile strength is obtained from this expression. And here what we do, we cast that cylinder, and then along the height of the cylinder, as you can see, this load is applied uniformly, and a reaction is developed at the bottom, and then it will actually develop a force in the orthogonal direction, and that causes a split at the middle along the diameter, right? So we can again find out the split tensile strength, and from that again we can also find out the property of this concrete used. Okay. Now beyond these values, there are two most important properties of concrete. Is the first one shrinkage and another one creep. That also we discussed in the last class. What is shrinkage? If you can recall, it is the change in volume due to loss of moisture. Okay, and that's what is called shrinkage. It is usually expressed as a linear strain, and as per IS 456, there is a specific clause 6.2.4.1. That clause says that shrinkage strain is 0.03%. Right. So in our estimation also, whenever we need this, we will use this value as recommended by IS 456. Now, we have also discussed some of the other features or characteristics of concrete, and the one is what we call durability, right? And if you look at the codal provisions, we have different exposure conditions for concrete. It may be mild, moderate, or severe. For example, if we construct a structure near marine environment, then obviously we have a severe environment because of seawater exposure. And then there are some recommendations for the minimum grade of concrete, as you can see. Now, for every grade, there is a minimum cover also specified. We have to follow these guidelines when we design using a specific grade. For example, if we use M25 concrete, then the minimum or nominal cover in millimeter is 30. That means we have to have this much of cover over the reinforcements. So the end of this bar to the extreme fiber, the distance between these two planes is what is given here. So for M25, it is 30 for M25. Likewise, there is a recommendation for minimum cement content and water cement ratio. This also we discussed that the water cement ratio when you prepare concrete is extremely important because that dictates the amount of workability we will have for that particular mix. So we have these guidelines and we have to follow those guidelines as we use different grades of concretes in our design. Now, all these recommendations comes with some rider. For example, if we use M20 concrete, then if the diameter of the bar is 12 millimeter or less, then we can reduce this clear cover to 15 millimeter. Likewise, there are some other guidelines also. When this will be necessary, I will update you accordingly. So let us move for the time being. We'll come to this point when we will take some design example. Now, beyond this shrinkage and durability, creep of concrete is also equally important. And what is it? It is time-dependent strain, right? When the concrete is under sustained loading, for example, we have dead load, distressing force. Under this loading, the concrete undergoes some kind of strain, and that is what we call creep strain, right? Now, in our design, we need to take care of this creep strain. But before that, if we go through the stress strain behavior, what we see, as you can see here, stress versus strain. So in the initial part, we have the elastic strain, and beyond that, we have this creep strain region. Now again, this is the idealized stress strain curve. In reality, it goes to the peak and then it goes down, right? But we have this idealized curve where the initial part is the elastic strain, and beyond that, we have this plastic strain due to this creep effect. Now, creep coefficient is ultimate creep strain divided by the instantaneous elastic strain. So, if we combine these two for this strain, which is actually dependent on time, so instantaneous elastic strain, as you can see here, so we are at, say, time point t here, so we have some instantaneous elastic strain, and beyond that we have the creep strain, and we have this ultimate creep strain which we have to take care in our design. Now, this creep coefficient theta, it depends on the age of concrete at the time of loading. So, if we pour concrete, then from that pouring concrete in the formwork, as time passes, the creep strain actually changes with time. Now, again, you can see these values at 7 days, 28 days, and obviously when we design the structure based on this 28 days strength, in our actual structure, we have to consider the effect of creep. Now, the point to be noted here, from this 28 days up to 1 year, you see we can still have the effect of creep strain, but obviously we will refer our values at 28 days. So, creep strain increases means theta increases, and ultimate creep strain decreases means the age of loading is increasing, as you can see here, right? Okay, now, so if we talk about modulus of elasticity, then again the stress strain curve, as you can see on your screen, it is not perfectly linear. So if it is linear, obviously we can find out the slope and then find out the modulus of elasticity. But in case of concrete, if we have this is the stress strain curve, then the question comes whether we consider the initial tangent, that means from the 0 up to this, if we have ultimate stress Fu by 3, that is the point where we define the initial tangent modulus, and that is the initial slope from this diagram. It is also known as the dynamic modulus of elasticity. Now beyond that, sometimes we define second modulus also. So it is the slope of line connecting the starting point and the point 1/3 of the ultimate stress. So it is also known as static modulus of elasticity. Now, if we refer IS 456, there is a very specific clause 6.2.3.1 that provides a empirical relation between the elastic modulus of concrete and the FCK value. This we discussed in our previous lecture. So we referred this expression to find out directly what is the modulus of elasticity of the concrete that we are going to use in our design. So basically what we need to fix is this FCK value for the concrete that we are going to use. Once we fix that, from that value we can find out the Young's modulus. Now, as I told you earlier that we have to consider the effect of creep, and then if we modify this EC, what we get here with the effect of creep, then we get ECE, and that is equal to EC by 1 plus theta. Right. Now, we can also define the slope of this tangent at any particular point, and that is what is called tangent modulus, right? But the point to be noted here is this EC value here, which is given in IS 456, and ECE the moment we need to consider the effect of creep strain. Okay. Now, before we move over to the limit state design, let us again just quickly go through some of the criteria that we follow when we test samples to find out the FCK value. Now, we cast cubes, and then each cube we call it a specimen, and then for different quantity of concrete there is a guideline that how many samples we have to test, and accordingly we have to follow these guidelines, and we have to first prepare the cubes and then we prepare them in a batch of 3. But there is a specific guideline, that's what I wanted to mention and draw your attention, that by chance if any of these say 3 cubes we have X, Y and Z, and one value it falls beyond this plus minus 50%, then we have to discard that sample, and otherwise we have to take the average. Now why that is the reason? Because if we have say a concrete mold of 150 by 150 by 150, although the concrete coming from the same batch, we need to carefully prepare this concrete cube, and for that we need to fill this in parts, and then every part we have to tam it with a tamming rod, and then finally fill the complete cube. Now in that process there may be some mistakes or some errors. Beyond that also we need to cure this cube properly. During that process also, if there is something wrong, then that will be affected in the strength, and sometimes we have this variation. That we have to keep in mind. Otherwise, if it is well prepared and well cured, then the standard option is we have to test these cubes, and then we have to find out the FCK value, as we earlier discussed, that we have to have 5% area on the left hand side of this value, and we have already discussed how to find out that. Okay. Now, beyond that, there are some acceptance criteria of the concrete as per IS 456. You can see the clause number here, 16.1 and 16.3, and these are some of the guidelines which we strictly follow when we use different grades. But let us not go through the details, but the only point here to be noted is sometimes for our design estimations, we, instead of testing the cubes and finding out the standard deviation, we use codal provisions for that. And as you can see here, the clause number is 9.2.4.2, and depending upon the different grade of concrete, code recommends the assumed standard deviation value. So for our calculations we can use, and then if the need be, we can test the samples and cross verify. Okay. Now as we progress further, we have defined the properties of concrete. Now we have reinforcement. The reason we have reinforcement, as you can see on this screen, if we apply a force P here, obviously the bottom fiber is in tension and concrete is weak in tension, and therefore there will be cracks here, and that's the reason we need to have rebars in the tensile zone, right? As you can see here, the moment we have rebars, these steels, they provide additional capacity against this tension, because steel is very good in tension, and that's the reason we have a combination of steel and RCC, right? Our task is to actually design this. That we'll do as we progress in this lectures. Now, different materials are actually used for this reinforcement. As you can see here, there are steel, the most commonly used material. However, sometimes we have alternate materials also, as you can see bamboo here, but obviously where you need higher capacities, we cannot use this material. The point to be noted here, any material which is strong in tension can be used as a reinforcement if that serves the purpose. However, in our entire study, we will only focus on steel and not the alternate materials, right? Now, when we talk about steels, we have different grades of steels. The first point to be noted is the diameter. For each diameter, we have the actual area. Then as we increase the diameter, this cross-sectional area increases, and if we use higher diameter bars, obviously it will provide more capacity against tension. Now, if we talk about the stress strain behavior of say mild steel, we get the observed stress strain behavior from the laboratory test is something like this. This is again a very schematic diagram, where we initially have this linear portion. So we can find out the Young's modulus just by taking this initial slope, right? Then as we progress, we have these different limits. We have first a yielding, and then there is a yielding plateau, and then again we have this nonlinear behavior which ultimately collapses at the point 8 F. And this is what is called fracture point, and this is the ultimate point, right? Now all of you know there is a property of necking. Actually it goes like this, but again we are not going into those details. That is not the purpose of this discussion. The point to be noted here, this is the stress strain behavior of the mild steel bar. We do not use mild steel in limit state design as we did in the examples of working stress method. In case of limit state design, we prefer to use what we call HYSD bars. HYSD stands for high yield strength deformed bar. Now, these bars actually having a stress strain behavior, as you can see here. Now, again, the limits are here, as you can see on your screen. So we have 0.2% strain. At the time of failure, we have this from 0.14 to 0.18. Now, for this HYSD bar, it is obviously less ductile than mild steel, and that's the reason you can see the difference between this curve and this curve. So, say from this point, from the point of yielding to the point of failure, we have a large region. And there is a plateau here, which is absent in case of HYSD bar. And that's the reason for HYSD bar, again what we do, we consider 0.2% proof stress to find out the yield value. So we have to find out Fy. So 0.2% proof stress will give us the value of Fy. Beyond that, these days all of you are familiar with a different type of bar which is called TMT bars. Now TMT bars stands for thermomechanically treated bars. Right. Now what happens when you treat HYSD or steel rods thermomechanically? These bars, they have a different region. The inner region, it is relatively softer and it provides the ductility. Then there is a middle part that provides strength, and it has an outer portion that is acting as a corrosion resistant. Now, in case of steel, it is the percentage of carbon that dictates different properties, for example, strength and ductility. But these are different bars we will use. For us, again, we will use Fe. Then, for example, if we write 415, then this is it represents the strength. So if we say Fe 500, so this is the strength of the bar that we are going to use. Now, let us quickly go through the working stress method. We have already discussed it is a modular ratio based method where we consider linear variation of strain, right? And that was the main, reference point with respect to which we define stress, and then we define the sectional capacity. Now, in this case, we define something called factor of safety, which is the strength of the material divided by the permissible stress, right? And modular ratio, as you can recall, it is the ratio of Young's modulus of steel and concrete. Now, in this method, what we do, if we have a cross-sectional area of steel, that with the help of this modular ratio, we convert it into equivalent concrete section. And so we basically convert it with the help of this modular ratio. And that is very handy so long we have linear variation of strain along the cross section. Now, we have solved some examples. It has certain demerits. Obviously, the first one, we need very larger section. Then another demerit is material properties are not fully utilized, right? Then we also have discussed some important issues like creep and shrinkage. In this method, we do not actually consider these important properties because we stay within this linear limit, and that's why it may become unrealistic if we consider secondary effects like this creep and shrinkage. That's the reason we have limit state method as per IS 456, and that is the main aim of this study. But between this working stress method and limit state method, there is another method called ultimate load method. We are not going into the details of these methods. Those who are interested can go through this concept. But again, the main point to be noted here is our interest lies with this limit state method. Now, why this is helpful? The first thing is, you'll see we will go beyond that linear behavior of strain profile across the cross section. That we'll see. And we'll consider the secondary effects as we progress. Here what we do in this limit state method, we consider different types of limit states. For example, we have collapse and we have serviceability. So we have limit states for collapse that deals with flexure, shear, torsion, compressions, and then we talk about limit state of serviceability that deals with deflection, cracking, and vibrations, right? So we have multiple limit states that is required when we go for this limit state design. You will see that in a minute as we progress in this course, because when we design a beam, for example, if you have a simply supported beam with point load at the center, it has a bending moment profile and then shear force profile. So we will design against flexure and we will design against shear, and we will see how we can use this concept of limit state method. Now, again, when we use concrete, our design strength is what? The compressive strength of concrete. In structure, there is a small difference between this statement and the strength of concrete that we get from the cube. So that value of strength of concrete in structure divided by the factor of safety, partial safety factor, and 0.67 times FCK is basically the compressive strength of concrete in structure, because when we test cube, it is 150 by 150 by 150. From there we get this FCK value. We reduce it by this factor to get the actual strength of concrete in structure. Then divide that by this material partial safety factor, and for concrete as per IS 456, it is 1.5. Therefore, ultimately what we get, the design strength of concrete in our case is 0.45 FCK value. So we start with the FCK value. The moment we define, say, M30 concrete, that is 30 Newton per millimeter square is the strength of the concrete. Multiply that with 0.45 and we get the design strength. So we start with uniaxial loading over cube. From there we apply a factor of 0.67 and then we again apply a factor of gamma MC, which is 1.5 in case of concrete, and then finally we get the design strength. So the approach is straightforward. Now, if we go for steel, again for steel, characteristic strength of steel is Fy. Note here we don't need to reduce that, we use Fy value, but we still use that partial factor of safety, gamma ms, which is 1.15. Now for concrete it is 1.5, for steel it is 1.15. The reason is, in case of steel, it comes from a production line where we have a better quality control, and that's why we have a lower value of gamma ms. Now if we apply this factor over this Fy, what we get is 0.87 times Fy, which is the design strength of the steel that we are going to use. Okay, now if we again recall the stress strain behavior of concrete, we get this 0.2%, and in case of mild steel, we have this type of behavior, but again we will not use this, we will use a different steel, and for that we have already studied the nature of stress strain curve. We'll go through that as we progress in our this week's lecture. Now before we go into those details, let us quickly also review the design loads. Now in case of limit state design, we have to consider different types of loads. As you can see here, we have dead load, then live load, then wind load, then earthquake load, and for each and every load component there are different factors prescribed in the code. For example, in case of limit state of collapse, if we consider dead load, our factor is 1.5. For live load, factor is 1.5. Then we have also factors for wind load, earthquake load. Now with the help of these loads for both collapse and serviceability, what we do, we make different combinations. The reason is, the structure may fail due to different combinations of load, and sometimes different loads are not work together. For example, if we consider earthquake load, obviously earthquake load and wind load, it is most unlikely to come and act over a structure simultaneously, and that's the reason code says that either you consider earthquake load or wind load. Do not consider this by, it is not a division. It is saying that either you consider wind load or you consider earthquake load, and then make a combination of loads. So we have dead load plus live load. Then if we have superimposed dead load, that also you have to consider. We'll go through all those different load categories and we'll make a combinations. But the point to be noted here is the combination of different loads, and we'll see in a minute that once we make these combinations, then we have to identify which combination is offering the worst case, and then we have to design the structure against those loads. Now, for example, say this, we have a retaining wall. So on one side of this retaining wall, we have this soil mass, and the wall is supposed to take care of this soil mass. Now, there are different types of failure that may happen. It may actually topple over this point, it may have a failure at this point, or it may altogether slide along this direction, because active earth pressure is acting over the wall and it may slide at the base. So these are the different types of failure we have to consider. Now, one thing you have noticed, that factor of safety for limit state of collapse is greater than the limit state of serviceability. Okay, so because when we talk about serviceability, it is dealing with deflection, vibration, cracking, and that's the reason when we deal with this limit states, the respective factors are less compared to when we talk about collapse, which is the point of failure. Now, let us quickly take this example, and for this retaining wall, it is safe in sliding and overturning with 90% of its weight. It must be safe with 100% weight. So what we do, we have restoring force or moment, then divided by disturbing force, and then we find out what is the factor available. And if this is more than 1, obviously our restoring force is more than the disturbing force, and then we consider it to be safe for obvious reason. Now, let us consider the design moment for a beam which is subjected to moment due to different loading. So, what are the different loading given here? We have dead load, then we have live load, then we have wind load, and we have earthquake load. For each load, we have evaluated the design moment, and that is given here. Now, we make a combination. Obviously, the first one is dead load plus live load, and we have the appropriate factors. And just by looking at that, you can easily sense this is actually the limit state against collapse. So, the first combination we have dead load, which is 100, and then live load, which is 50. Both of them are multiplied by respective factors, which is 1.5 here. And then once you add them, we get the design moment corresponding to this load case. Say this is the first load case. Similarly, we have other load combinations, and let us mark it. This is the second load case, and then we have third load case, and then fourth load case. For the timing, let us consider these 4 load cases. Then for each load case, we find out what is the value of the design moment. Then just by looking at these values, you can see out of all these 4 different load cases, we have the second load case, which is dead load plus earthquake load, is offering us the maximum value of bending moment for this beam. Therefore, in our design, we have to find out the capacity against this requirement. So if we design the beam, we have to design it against this value. Now, as we progress in a structure, a different section may have a different load combination offering a design value. That we have to figure out before we start the design. In this case, the critical load combination is dead load plus earthquake load. Now, with that background, let us see what happens when we consider the deformed profile in limit state of collapse inflection. Now, obviously, we have this neutral axis here, and as we progress from the neutral axis, we have the variation of strain, and if it may be linear, it may be nonlinear depending upon the situation. But one point to be noted, it is 0 at this neutral axis. As we move away from the neutral axis, its value increases. Not only that, we have the stress strain behavior for concrete. If you recall, it is the FCK value corresponding to this 0.2% strain. And then in case of steel, what we do, we start with this idealized curve. In case of concrete, let us consider, we'll consider steel in a minute. So from this actual curve, we start with this idealized curve, and then idealization is done beyond this point. So the moment we reach 0.2% strain, beyond this point it is linear. That means we have this FCK value reached. Then what we do, we first reduce it by this factor, because from cube we have to go to the actual structure, and the factor is 0.67 if you recall. And then we apply this partial safety factor, and what we get is basically the design curve. So this is the curve we will use in our design the moment we consider the moment of resistance of a particular section in limit state method. Okay, just recall this expression, and we will actually use this profile in our design as we progress in this lecture series. The point to be noted here, this value here, which is 0.67 FCK by the factor of safety. Factor of safety is 1.5 if you recall. And then we have a combined factor, 0.67 by 1.5 times the FCK value is the limit. And this point corresponds to 0.2% strain here. At the time of failure, the strain is 0.0035. So these are the features of this design curve we need to remember. We will use that in our further discussion on limit state method. Now, in case of steel, we have mild steel. For mild steel, again, this is the actual curve. That actual curve we idealize with the help of this curve. So what we have here, initially it is linear. Then after certain time, when we reach this Fy value, the curve is straight, as you can see. Now, this idealized curve is then reduced to design curve. How do you do that? We apply again a factor 0.87. So 0.87 times Fy is design curve, and from there we can also find out the slope, initial slope, which is 0.87 Fy divided by the strain at this point. So this is the strain corresponding to 0.87 Fy. This is 0.00108, and then if you do that, in case of steel, we have, this is the Young's modulus. Now, as I already told you, we're not going to use this mild steel, so we'll not use this. So what we'll do, we'll use HYSD. And for HYSD, again, the stress strain behavior, actual stress strain behavior is shown here. Now, because there is no sharp yield point here, what we do, we consider 0.2% strain. Then we draw a parallel line with a slope, if this is initial slope is theta, with that line, and the point we get here is actually the yield point. Then what we do, we develop the idealized curve that you can see. The moment we get this idealized curve, we then reduce it to design curve with the help of this factor Fy divided by 1.15. Then we have this reference point I have already explained, because that tells us the yield point. So what we do, in case of this yield point, we find out the respective strain. For that, what we do, we drop this vertical line, and the point here corresponds to the strain to this value of Fy by 1.15. Now, for that, what we do, we add these two strains. So initially we have 0.002, and then this part we can easily find out this amount of strain. So the stress is 0.87 Fy divided by S, right? And effectively this is the strain at that particular point. In our again design, when we'll consider this HYSD bar, you'll see we'll use this idealized design curve for stress strain of this HYSD bar, and then using this we will find out the moment of resistance of a particular section. The point to be noted here, this value of strain. So this is the strain in steel. This value of strain we'll stick to, and we'll try to use this to its maximum. So in our design, we'll see that at the time of failure, we'll have at least this value reached, so that the property of this steel is fully utilized. That will ensure. So these are some of the features to be noted as we progress in this course. First thing is, for concrete, the idealized curve here, which is initially parabolic, then straight line. The respective design value is 0.67 FCK by the factor of safety, which is 1.5, and the strain limits are 0.002 and 0.0035. That is the point of failure. For steel, it is HYSD bars. So for that, the value of strain is shown here. And I have already explained how we get this. It comes from the idealization first, and then we apply the factor of safety, right? And then we get the design curve, and from there we evaluate this strain. So we'll try to ensure that the strain in the steel attains this value when we have respective concrete stress or concrete strain. That we'll see how we can manage that in our formulation. But these are the two main things we will use in our estimation of sectional capacity. So with that, let us close here a brief overview. But these are the two features that in our next class we will use to develop the sectional capacity formulas, and then we'll see how we can design a cross section against certain value of bending moment. Right. So go through this derivations or notes, and then if you have any query, you can drop us a mail, or in our open session, we will discuss that. Thank you very much.